Before we go back to our motion model and how we can simplify the relations between the states and the given values, I want to introduce the first order Markov assumption. Assume you want to estimate the posterior distribution of pxt given all previous states, and you have no observations or controls. So this is a pretty simple example, but it works fine to explain the Markov assumption. You can write this distribution as the following. This relation can be represented as a chain. For example, to estimate or predict x1, we only use x0. To estimate x2, we use x1 and x0. And finally, for x3, we use x2, x1, and x0. In this example, the Markov assumption postulates that x2 is the best predictor for x3. This means that the other states x1 and x0, also future states, carry no additional information to predict x3 in a better way or more accurately. We also say the state x2 is complete. We remove the links or connectors between x1 and x3 and x0 and x3, which means x3 is independent of x0 and x1. It only depends on x2. And of course for x2 it is the same. This means you can also remove this guy over here. Since we now assume that xt only depends on the previous state, we can rewrite the posterior in this way. So if we want to continue this chain, which means to predict the future, we only take x3 into consideration. An example could be a weather forecaster. The weather of tomorrow only depends on today, and today includes all previous information and is uncertain, of course. As an important fact, we have to assume that we have an initial guess for x0. So x0 must be initialized correctly. Let's go back to our motion model, and I will show you how we can benefit from the Markov assumption. Before I talked about the Markov assumption, I stopped here and asked you how we can simplify this structure. Now I will show you how the Markov assumption can help us here. First, I split the control vector into the current control, ut, and all previous controls. Now let's take a look to the first term. The probability distribution of pxt is conditioned by xt minus 1, all previous observations, all controls, and the map. Here we apply the Markov assumption the first time. Since you already know xt minus 1, z1 to t minus 1 and u1 to t minus 1 will not carry additional information to predict xt in a better way. These values were already used to estimate xt minus 1. This means xt is independent of these values. Because of this fact, we can remove these two conditions in the graph. This will result in the following. And the posterior distribution of xt only depends on xt minus 1, ut, and the map. This term is called the transition or system model, which predicts or which moves the previous state in the new one. And as you can see, we do not need the whole observation or control history. Here you can also consider that the map M does not influence xt. It is common practice to neglect M, but here we keep it. The second term describes the posterior distribution of xt minus 1 given all previous observations, all controls, and the map. Here we use the Markov assumption again. We assume that ut tells us nothing about xt minus 1, because ut is in the future. We ignore ut to estimate the state xt minus 1 and remove this condition over here. Based on this assumption, we rewrite the motion model again. After these two steps, we achieved a really important step. I ask you, do you know why?